Okay. Good afternoon, everyone. Good afternoon from my time zone, and welcome to this technical briefing. My name is Xavier Frank. I belong to the Technical University of Catalonia, and I will be chairing this technical briefing, which is entitled Reactive Systems with Spectra, a tutorial. It is a hands-on technical briefing, so be ready to exercise and to participate actively during the session. The two presenters of this technical briefing are Shahar Maoz from the Tel Aviv University and Jan Oliver Ringer from the School of Informatics and University of Leicester. They will share a screen and manage completely the session, and they will interact with you as they deem necessary during this session. So without any further conversation from my side, I give the word to Shahar and to Jan Oliver, and I hope that you enjoy the technical briefing.
Okay, great. Thanks a lot. So welcome to this technical briefing. We have pre-recorded short videos. So what we will do is we will play these videos with the content, and then you can put questions in the chat. And after 5 minutes or so, when the video ends, we will be able to answer questions. So just feel free to ask questions in the chat at any point in time. And there's also some material I think that Shahar wants to post in the chat. So there will be a live exercise part. So for that, you will need to install the environment if you want. But of course, I will also be having the environment open, and we can do all of your questions, all of the things that you want me to try out on the environment. We can do that live. Okay, so we're just going to start with an introduction.
Welcome to our hands-on tutorial on reactive synthesis with Spectra. Before we start, what is reactive synthesis all about? Reactive systems compute by ongoing interaction with their environment. They include sensors that read input from the environment and actuators that hold the system state and represent output. When we model the behavior of these systems, we consider infinite runs. That is, these systems are not supposed to halt unless someone turns them off. How are these systems typically developed today? The typical development of reactive systems today consists of several phases: formulating the requirements, some formal specifications and models, an implementation, a lot of testing, and maybe some formal verification. However, despite iterative processes and excellent advances in testing and verification, behavior over time is difficult to implement correctly. At a very high level, both formal verification and testing look like this. We have a tool called a verifier or some test execution mechanism. We give it as input a program or a model representing the implementation, and a spec or a set of tests that represent this specification. The verifier runs and answers yes if the model or program satisfies the spec, and no otherwise. Test execution runs and answers yes if the program passes the tests, and no otherwise. So, in both testing and formal verification, we first create a model or a program, and then check whether it satisfies the specification or similarly passes the tests. In other words, we describe the what, we describe the how, and we put them one against the other. Synthesis is different. In synthesis, we have a tool called a synthesizer. The input for the synthesizer is just the specification. If possible, the synthesizer outputs a model or an implementation that satisfies the specification. It outputs no if no such model or implementation exists. So in synthesis, there is no upfront investment in building a model or an implementation which may or may not be correct. In other words, we describe only the what. The how is computed by the synthesizer. Reactive synthesis is an automated procedure to obtain a correct by construction reactive system directly from its temporal specification. Spectra is a specification language tailored for use in the context of synthesis. The language comes with Spectra Tools, an Eclipse-based IDE that includes, beyond synthesis itself, additional analyses and tools to help engineers write and use specifications for the implementation of reactive systems. So today, in this technical briefing session, we present an introduction to the Spectra language and tools from the engineer's point of view. We don't talk about how Spectra is built, the algorithms it uses, etc. We talk about the perspective on the engineer who uses Spectra, writing specifications, synthesizing an implementation, and executing it. No background in formal methods assumed or necessary. Some examples of the reactive applications developed by us and by our students using Spectra include classic puzzles like Towers of Hanoi, moving obstacle evasion, and Cinderella and her wicked stepmother, as well as simple Lego robots, one that sorts bricks by color, an elevator, and various simulations for a smart home, a four-way junction, and parking lot operations. So here's the plan for the next 2 hours or so. We have pre-recorded 9 short modules divided into 3 types: language, analysis, and execution. Each module is about 10 minutes long and ends with a short suggested exercise. After each module, we will give you 2 or 3 minutes to try out the exercise. This would also be a good time for us to answer questions that you can ask on the Zoom chat. After 2 or 3 minutes, we will show the exercise solution, answer questions, if any, and then move to the next module.
Welcome to this tutorial on React. Yeah, so this one was already the first video. I don't see any questions in the chat. So we would just continue with now the installation instructions. So if you want to follow the tutorial live, then these installation instructions are for you. The instructions are maybe just 4 minutes. Downloading and installing might take a little bit longer. And yeah, this is something you could probably do in the background while we just continue. So if you don't want to install it, that's also fine. And we will show tasks and solutions for each one of these units live then. Synthesis with Spectra, and we start off with the setup, how to install Eclipse, how to configure it, and how to import the projects into the workspace that we're going to use throughout the technical briefing. So we just go to the download page of Eclipse, and then you can download the installer. This will make sure that you also get a Java runtime installed. So we'll just download this file quickly, and then we can start it. So if you have a recent version of Eclipse already installed, you might be lucky and you might be able to install directly the plugin into that Eclipse, but we would recommend that you maybe download a fresh version of Eclipse. Yeah, so this is the installer. I just started it, and the package that you should install is this Eclipse IDE for Java and DSL developers. You can reuse an existing one or install a new JDK, and then yeah, just find some installation folder and then say install. I think you have to accept some of the Eclipse licenses and licenses of the other Eclipse projects. It will download the Eclipse in the background. This might take some time. Okay, now the installation was successful, and I think we can just say launch. Then it should open this very fresh Eclipse with probably some default workspace. So yeah, let's just take a default. Let's close this welcome screen and then import some projects. So we'll just say existing projects into workspace. and we will import it from the archive file available for download. So I already downloaded this in my downloads folder, the Spectra tutorial. It has quite a few projects because we have one project for every module in the briefing, and then we have optional solution projects for some of the modules where a solution is available. Just click finish. Yeah, we have the projects here, but now you see that it doesn't recognize the files. It just opens them in some external editor. So what we need to do is we still need to install new software help, install new software, then select the Spectra update site. The update site is this under this URL. So I'm just going to copy this, and yeah, we can add a new update site. And then it should find these sub packages, so you can just select everything. We don't need exactly everything, but we need most, so yeah. A few times next, accepting some licenses, and then now we also have to agree to install the unsigned content and restart the IDE. Okay, so after restarting, we can just check whether now the Spectra specifications are recognized. Yep, that looks good. So let's quickly check the preferences. Here under Spectra, we have some settings to make. So if you are on a Mac, the CDD version will not work for you. You will have to select JTLV package. The rest we can just leave. We will later play with some of these settings, but the main thing, if you're on a Mac, select JTLV here, and that's it. Okay, so this was the installation instructions, and if you have any trouble installing or troubleshooting the installation, then I'm going to paste a link in the chat, which is to a Microsoft Teams room where one of our PhD students will be waiting and helping you with the installation if you have any questions. Otherwise, I think we can probably just continue with writing our first specification. Okay, welcome to the first module of this tutorial. First, we will learn how to write our first specification. We will look at variable declarations, assumptions, and guarantees. And the example that we're going to follow is these two examples. One is a traffic light example, and the other one is a grid world with a robot moving between grids. But first, we have to see how to create our first Spectra project. We can simply right-click and say New, Other, and then select under Other Spectra project. So this is how we would get a whole new Spectra project. Let's call it first project and finish. Now we have this first project and it already has a first specification. The specifications, they always start with spec and then the name of the specification. And then we can have, for example, variable declarations and guarantees and assumptions. So let's create a new specification. We can do that in any Spectra project. So let's create one here. And now we will create a new other just the Spectra file because we already have a project. And we can call it maybe traffic L1 because that is the one we want to create. This is our first example. So here we're going to model this traffic light system. There are basically two lanes, A and B, and we have two traffic lights. So let's say we want to model two variables, one that tells us whether the traffic light is green on this lane A and the other one that tells us whether it's green on the lane B. So these are variables that we would usually say are system controlled because we want the system to control the traffic light, and then there's also the environment. The environment in this example would control the cars that are driving here. Let's delete these guarantees first, the simple one. And now let's say we wanted a system controlled variable. This is the one where we want to synthesize the control for. So we will start it with sys for system. Then the type, the data type here is simply Boolean. And then we can say green A. This is the variable that tells us that on the A road, the traffic light is green, and then we have the one that tells us on the B road whether it's green. Now, this is for simple variables. We also can have environment variables. These are the ones that the system usually senses, or something that happens outside the system that the system is then notified of. So here we would say maybe an environment variable, also of type Boolean, can tell us whether there is a car in the street A or in lane A, and then we might also have one for lane B. And then of course we want to maybe relate these inputs, these environment controlled variables, with the outputs, these system controlled variables, because, well, clearly if it's a traffic light, there's probably some relation between whether there are cars and whether the light will be green. Now, the obligation of the system, we usually describe it in, or we always describe it in guarantees. And in Spectra guarantees, we would have the keyword gar, and then the guarantees can have different types depending on their temporal meaning. So we could have guarantees that only have to hold in the initial state. So this would be guarantee, ini, and then let's say maybe we want to have green A, we want to have both turned off, both lights not green, so not green A and not green B in the initial state. Then later we might want other guarantees. So for example, we would like the guarantee that always, so this would be now a safety guarantee, something that has to hold in every state whatsoever. Always, we basically don't want green A and green B to occur together. The lights should never be green at the same time. So we negate that A and B are both green at the same time. Then we might also want some further guarantees that there's actually something happening in the system, some liveness guarantees. So this guarantee could be always, eventually, we want the maybe green A to be true. So after some finite amount of time, always we want to see that the left lane has a green light. So these are the three kinds of temporal operators that we have in Spectra: the ini, the always, and the always eventually, and they always have to start a guarantee or assumption. So what we wrote here for guarantees, we can do the same for assumptions, and then it would be ASM for assumption. And now let's see what is a good assumption. I mean, we can do very, very similar assumptions here, that initially there is no car, or maybe that initially there is a car. So let's say maybe initially there is a car at A and not a car at B. So this is, yeah, quite arbitrary and maybe not a good assumption, but this is how these assumptions would work. And we can also have, similarly as we could have for the guarantees, the three temporal operators, we can have those same operators for assumptions, and then always also write safety assumptions, and also write these liveness assumptions. Okay, so this would be our first example of the traffic light, and we saw that all the data types, they were just Boolean, so we can do a bit better. In Spectra we also have other kinds of data types. Let's create a second specification in this same project. So this would, we would call it the grid L1. And here we want to model this grid world of the robot. So yeah, well, here it's a simple 5x5 grid. So with booleans, doesn't make much sense. We could of course have one boolean for every cell. That probably wouldn't be a good idea, because the robot can only, we want to model a robot and we want to model a robot position. So let's say we have a system variable, or maybe an environment variable, and the environment will tell us where the robot currently is. And now we want to represent the position in x and y coordinates. So we would need an integer that goes from 0 to 4. So then we have these 5 cells, and we can call it yeah, maybe just robot x, and then we can have a similar one for robot y. And then we might have also some system where that wants to move the robot. So we would then have a system output variable. And now this one can have maybe an enumeration data type. So the robot could maybe move up or down or left or right, or it could just stay in place. And this is the variable system variable move. So here we see bounded integers and also enumerations. And then the way that we would use these is that maybe in assumption, in an initial assumption, we say that the robot x is 0 and also the robot y is 0. So yeah, this would mean something like that the robot is initially in this corner here, and then we can also of course relate them. We might want to have an assumption that says always when the robot says it wants to move up, this would be move equals up. This would imply, so we can write implies like this, or we can also write implies if we want to type a lot. Move up, this would mean, well, if we say top left is 0, 0, then moving up would basically decrease the y coordinate. So this means the next y coordinate would equal robot y minus 1. So every variable that is in the context of next would be in the next state already. So we basically say here that the variable in the next state is y reduced by, is the current state variable reduced by 1. And this next operator, this can be used in the safety assumptions and safety guarantees. It is important that we can not talk about the next value of a system variable in an assumption, because this would mean the environment would have to look into the future, and that's not possible. So here we can, but here we are only talking about the next environment variable, and well, the environment of course has control over its variables, so this is fine. So this would be an update of the robot coordinate based on the move that the system wants to do. And we would probably need very similar ones for the other kind of moves to make sure the robot moves correctly, to have our assumptions that the robot, when it moves, that the environment will make sure that the robot ends up in the right grid cell. Okay, this is a very simple overview, very short overview of the different kinds of variable types and how to use these variables, how to use the different types of Boolean, bounded integers, and enumerations. And now there is a task for you. So please go ahead and extend the specification grid L1 that we just created with the following guarantee, which says when the robot is at the end of the grid, it does not try to move outside. And then also in the next step, try to extend the specification of the traffic light with the following assumption that always eventually traffic will arrive at each light. Okay, so the first task was to Okay, great. So this was the first specification for us, and you can see that these don't know why it went black, would be helpful. So you can see that in your Eclipse, in case you installed it and imported it, we will have folder L1, and we will have exactly those two specifications. And they also have the task written inside so that I don't have to keep the slides up for while you're trying it. And now we would take the time while you work on this task, we can answer some of the questions. There were some very interesting questions in the chat. So I'll just go back a little bit to the first one. So there was a question whether with guarantee we specify constraints or invariants. So the important thing is that with guarantees, so an always guarantee could be seen as an invariant because it has to hold in every single state. But for example, if the temporal modifier is initial, then it's not really an invariant because it only has to hold in the very first state when the system starts. And similarly, the always eventually, this is something that has to repeat after some finite time. It has to happen. So it's also not an invariant in that sense. So the safety guarantees, they are invariants because they will hold in every single state. Then there was another question about the difference between assumptions and guarantees. So I think that maybe the traffic light, yeah. So well, for this one, it's very clear that the responsibility of not turning both lights green, this is only something that the system can do because the system is the one controlling the variable of green A and green B. So when it's about controlling specific variables, then it's usually either an assumption or a guarantee. So who is responsible of doing it? The guarantees, the system is responsible. Now for the grid world here, the environment controls the coordinates and the system controls only what move it wants to make. So what we have to do is we have to write many assumptions, or we have to write assumptions that characterize how are the coordinates going to update based on the move that the system wants to do. Because if there was no, like we have to assume that if we want to move forward or up, then the environment that we issue this command to will really make sure that we move forward or up. Otherwise, when we have more complex tasks, there's no way to satisfy them if basically the environment would place that as at random. So then we have this clear distinction between assumptions, because this is something that will happen to the sensors and the environment and changes that the system can do to the environment. And the guarantees, this is what we really want the system to realize. And in many cases, it's also clear that, of course, we can only realize some guarantees if the assumptions hold. So if this assumption that moving up would decrease the coordinate, if this doesn't hold at some point, then how can the robot guarantee that it moves to a specific coordinate? So this is I think this is maybe with these examples, it's a bit more clear, and we will have more examples where hopefully the distinction becomes very clear as well. And then there was an interesting question about uncertainty. So there is no built-in mechanism for uncertainty in these specifications, but you can use, for example, under specifications. So you could specify that the moving up updates decreases the y coordinate, or it doesn't, right? But then you might want a little bit stronger guarantees. So we don't have any anything of probabilistic nature in Spectra. But you could have something that we will see as one of the more advanced patterns. This would be that you assume that eventually the robot will be at the different place. So this is very, very useful when you build real robots, because the physics of the world, they don't work in like one computation step. So when you move up or move forward, then it might take some time until you are at the next grid cell. So then you want to have an assumption that eventually you will be there, so that then you don't know how long it takes, but you know after some finite time it will happen. Okay, yeah, very good. So if there are no more questions, then I think we can also.
Can I ask one more question?
Yep. Yes, please.
This clarifies a lot of things that I didn't know. What if the number of states are too large, and then this manual tasking of specifying the assumption become very, time-consuming, isn't it?
Yeah, so you will always try to specify assumptions. I mean, there are ways to write good specifications and bad specifications. And for example, one thing we realized when we started teaching writing these specifications to our students is that some students try to think in a very imperative way, and they try to really say detailedly, okay, when this happens, I want the robot to do that. But that's actually then difficult, because this way you add many constraints, and you can have inconsistencies between your constraints, and then you have a problem. Then the specification becomes unrealizable. So you will always want to try to write things on a high level, basically only by writing what you expect from the system and not how it should work. But that's a huge challenge for new specification writers, because when you program, you think about how it should do it.
Yeah, that's right. And does it have other tools to, for example, identify the inconsistency in the specification? Do you have such tools?
Yes, yes, we do. So I don't know if I can bring up the outline. Do I have the outline here? Well, we had the outline in the chat. Shaka posted the outline. So we have these analysis tools. So one is the Synthesize, which can also check whether it's realizable or not. And then Unrealizability is exactly this, which detects inconsistencies between the guarantees, for example. And then there's also something, the non-well separation, which does similar things, but in a more complex way for the environment. So this is basically checking the kind of the quality aspects of the specification. Yes, so that's one of the main things that we have been working on in this Syntech project. Actually analyzing, making the specifications, making it possible to work with the specifications, not only write them and hope for the best, but also to do this kind of debugging. Yeah.
When it synthesizes, it produces like a C code, something like that we can deploy.
So that how to deploy it, this will be part of the second E2. That's the how we will execute it on systems. So right now we have wrappers written in Java, but then you can have a JSON interface or other HTTP interfaces that we used. So we can basically run it on robots that have code written in Python or C++, and then just ask via some maybe JSON interface to ask the controller what do I do next. So basically this is what I sense right now. So then please compute what should I do in the next step, and this is how we usually do it. So we also had some robots which are controlled by simple microcontrollers because they are much cheaper, but then you have an HTTP connection to actually get the the interpretation of the controller of the synthesized system.
So eventually we get one controller where we can interact with them, you know.
Yes, yes, yeah. And we will see how to do it. So we will develop two kinds of applications. We will now develop them in Java, but then you can easily see how to extend it to other programming languages. Yeah. This will be in E2.
Cool.
Okay, great. Yeah, now if there are no more questions, then we're going to go to the solution, actually. Task was to extend the specification grid L1 with a guarantee that when the robot is at the end of the grid, it does not try to move outside. So to do this, we go back to the specification. And what it means to be at the end of the grid, this is basically these coordinates when they are at, well, 0 or 4, so that they are at the boundary of the grid. And we need a guarantee for that, and we want this guarantee to always hold. And then we can start with the different cases. So let's say the robot X is 0, then this implies that we want the move not to be left. And then we have another case where the robot X is 4. But now it is quite important how we use these operators here, because AND binds stronger than implies. So what we need to do is we need to put this in parentheses, the different cases, because otherwise the AND would probably bind, yeah, this move not left and the rob X. So the equality binds stronger than the AND, but the AND binds stronger than implies, so we need to put some parentheses here. So yeah, rob X equals 4, then we don't want to move right. And then we have a very similar thing for the y coordinates. So if we are at y0, then we should move up, and if we are at y4, then we should move down. And this is it. So the next one was to extend the traffic light specification with the following assumption that always eventually traffic will arrive at each light. So we had these variables car A and car B. And we're now going to add new assumptions. So if this was an always eventually assumption, so very clear which temporal operator we use, the liveness one, and then we could write car A and car B, but this would mean that always eventually at some point in the future car A and car B will arrive at, well, the A light and the B light. So maybe we don't want that. Maybe we want something more flexible where we say that we can have always eventually a car at A and a car at B. So we would have to write this in two separate assumptions because they can both independently occur. Okay, so welcome to the first analysis of our... Yeah, so I guess there were probably no more questions about these simple solutions to the tasks. If there are no further questions, then we're just going to continue with the second one, with the second unit now on synthesizing our first controller. To the first analysis of our specifications, and this one is about synthesizing your first controller, and we will see how to synthesize controllers and also check realizability of specifications, so checking whether there exist controllers. So we'll go back to our example of the traffic light. I just rearranged some of the assumptions here, and now if we want to synthesize a controller, we simply right-click in the editor, go to the Spectra menu, and then we can say synthesize a concrete controller. And what this will do is it will print an automaton on the console here. This one that tells us how the system here would be implemented. This system will make sure it satisfies all of these guarantees when these assumptions are satisfied. Okay, so there's one initial state which has car A true and B false as the input. That is expected because that's the only initial state that the environment provides. And then the output is false and false for green A and green B, which also makes a lot of sense because it satisfies this initial guarantee. Then we should never see an output where A and B are true together, which also is the case. But then we see actually that we only have a single state here, and in this single state, no matter what the input is, the output is always that green A is true, because that is also our liveness guarantee that we need to satisfy. And then green B is simply false because we have this safety guarantee here that A and B are never green together. So we could add, to make this a bit more interesting, we could also say that we want green B to be always eventually true. And then we can synthesize a concrete controller again. And now we see it's a little bit more complicated. Well, now we just have two states where it just keeps track of the different lights. And in one of them, B is true, and in the other one, A is true. And then it alternates between this S0 and S1. So that's still very simple, but actually we just said here that the lights should be green always eventually, but what we really want is that the light is green when there is a car, right? So maybe we should write something like this, that there's a car in A and that A is then green, and similarly here there's a car for B and B is green, because otherwise, yeah, it doesn't really make much sense to have the lights green. Or yeah, we could also write something maybe similar, just let's write it with some safety. So let's say that always if there is no car A, then we don't have the light A green. So this is basically avoiding that we have green lights when there is no car, and we can do the same thing for B. So now let's synthesize a controller again, synthesize concrete controller, and it tells us actually there is no controller. It can't implement this. There is no, the specification is unrealizable. And this is maybe a bit confusing, but we can also check the realizability directly without synthesizing a controller, and it tells us, well, it's unrealizable. And here, in this case, it's unrealizable because now what could happen is that there's never a car coming. So if we put back our assumptions from L1, this was always eventually car A, and always eventually car B. Now we have always eventually cars coming, so then we would be allowed to make the light green, and this way we should hopefully be able to satisfy these guarantees. So now let's check the realizability. Check realizability, save it. Yep, now it's realizable. And now we should have a nice controller again that makes sure it gives a green light when a green light is needed. Okay, great. Now let's look at this grid world here. Let's see what happens when we synthesize a concrete controller here. It also does a controller, but now actually what happens is, because we have this grid, there could be lots of possible inputs, and there can be many states. So if we even increase the grid size, let's say not to 4, but I don't know, maybe 20, then what happens is that the controller quickly gets very large and we have trouble printing the controller because it gets really, really large. So in these cases, what we would want to do is we would just want to check realizability, because this is much faster and it tells us, well, specification is realizable. That's it, done in a few milliseconds. If we synthesize the concrete controllers, it will take some time. I'm not sure that it prints the time, but yeah, you see, it takes even 3 seconds just for printing and formatting all this. So here, really just checking realizability is much faster. And then we can also synthesize something called a symbolic controller, and this will just put out a representation of the controller, which is also really fast, and it doesn't require the printing on the console, but it is machine readable, so later we can execute that easily. So we don't only have the concrete controller, because for large state spaces with large inputs it doesn't make much sense to have the concrete controller. We also have this symbolic controller. Okay, now this is the task. So we have two further specifications which are based on the traffic light specification that we just saw, the traffic L2A and the traffic L2B, and they combine liveness assumptions and guarantees into one, and for each of them please check whether they are realizable, and if so, synthesize the controller and then explain either why the specification is unrealizable or how it realizes the specification. So we'll have a quick look at these. This is the A, and it basically takes the two liveness assumptions and combines them into one liveness assumption, doesn't change anything else. And this is the traffic L2B, and this, in addition to the liveness assumptions, it also combines the liveness guarantee into one. And now please check whether they are realizable. If so, synthesize the controller and then explain how they realize the specification or why they might be unrealizable. Okay, so let's.
Okay, yeah, so there was an issue in the video. The folder name is actually a different one, so it's not the L2, it's A1 first controller, but then the specifications, they just contain the name of the folder in your workspace. So yeah, these are the ones to look at, and they are exactly like the ones in the video. So if you want to have a look, maybe for 1 or 2 minutes to play with the realizability checking, then you can do that right now. And if there are more questions, then please post them in the chat, or just ask your question right now if you want. If you want me to try out anything here on the screen live, then I can also do that. So then just yeah, unmute yourself and ask your question if you want.
It's somehow strange that when I'm trying to check the realizability, it always says that the specification is unrealizable, even with all examples that you have. Maybe.
Are you on a Mac?
Yeah, I'm on the Mac.
Okay. Yeah, we didn't have a Mac for development, so it could be that there's an issue. If you check under Window Preferences and then go to Spectra and then check which BDD engine is selected. So you could try to select here JTLV package.
Oh yeah, I didn't change that. Yeah, let me apply that.
I mean, it could be that there are quite a few bugs for Macs. So I hope that
Now it fixes. It says that.
Great. Okay, good. Okay. Yeah, so I think we can also maybe just look at the at the solution right now. And if there are any questions, please, just go ahead. You can. There are not so many people talking in the call, so just you can also just unmute yourself and ask.
Let's have a look at a solution to this task.
We were checking whether they are solution to this task. We were checking whether the two specifications are realizable, and if so, synthesize the controller and explain how the specifications work. So the first change in specification 2a was to combine the justice assumptions that car A and car B always eventually happen, and that they then happen at the same time. Now let's see if this is realizable. Spectra, check realizability. It says it is, and we can synthesize a concrete controller. That's easy. So what we actually see here, that car A and B now always eventually happen at the same time. This is something that would also satisfy the two assumptions that car A happens eventually and that car B happens eventually. So this is just a special case, a little bit more specialized than the two independent assumptions. But the two independent assumptions could be satisfied by exactly the same kind of environments. So it's no big surprise that this is also realizable. And we see here in the strategy how it works. So initially we go to state S1, and then basically you see that S1 sometimes goes to S0, but sometimes stays in S1. So actually the cases that we're staying in S1 are the cases where there's no car for A. So we are basically just waiting for a car on A. And while there's no car for A, we stay in S1. Then if there is a car for A, we set the light for A true, and then we go to S0. And in S0, we basically do the same thing, but now we are waiting for a car for B. And only if there's a car for B, we set the light to true and then go back to S1. So basically this way, we are kind of alternating between waiting states, and that is completely fine, because saying always eventually, I mean, in theory there would be cars queuing up if only one car would ever pass. But here in this case it doesn't really matter, because we know that enough cars will always be coming to satisfy A and then B and then A and then B. So this is what the strategy for this controller is doing. Now let's look at 2B. Let's check realizability first, and it says it's unrealizable. What happened is that the guarantees here were merged as well into a single one. And now this basically, instead of always eventually green A and always eventually green B, we now say always eventually green A and green B. The reason is that this is unrealizable is because it simply contradicts this safety guarantee, which says A and B are never true together. And this one was basically saying that A and B happen together after some finite amount of time. So, and that over and over again. So this is clearly something where we have a contradiction between this liveness and this safety that rules out any states where green A and green B happen at the same time. So welcome to this module on basic. So just if there are any questions, feel free to post them in the chat at any point in time. And if there are no questions in the chat, we will probably just continue with the next module. And this module now would be the step-by-step simulation. Step-by-step simulation of controllers. And what we're going to look at now is how we can explore the controllers that we have synthesized. So we have already used this specification of the traffic light. I think this was in 1 or 2. And we already did this synthesize a concrete controller, and then we have this kind of transition system here. What happens when controllers or when specifications get larger is that also controllers get larger. So maybe this one here, if we want to synthesize a concrete controller, it gets a bit more complicated to follow the behavior that is synthesized in this controller, and easily the specifications that we're dealing with, they can have thousands of states. So then even printing the transition system will no longer work. So in that case, what we can do is we can synthesize a symbolic controller, and that is also how we execute the controllers in most of the cases when we run them on robots or when we run them in our own programs. And the symbolic controller, we can simply say Spectra synthesize a static symbolic controller. We will have a look what the just-in-time symbolic controller does later, but right now what we need to do is synthesize static symbolic controllers. So we can synthesize a static symbolic controller. We will see that it says controller is saved to disk. It's quite quick. If we refresh the project, we see that there are 3 files in the out folder, and this is a representation of the symbolic controller. There's really, it's an internal BDD representation, so there's not really much that we can do with this. It's some numbers and nodes of the internal representation. So there's not really any way for us to inspect this by looking at the transition system, because the transition system is a formula represented as a BDD. So what we need to do is we kind of want to still explore this controller because we want to see whether it makes sense, or we want to see what happens when the environment gives certain inputs. So what we can do is there is an add-on in Spectra, which is the rich controller walker, and we can decide to walk this controller as the environment player. So here the environment is controlling whether cars are on road A or B. So if we want to walk this as the environment player, in this dialog, what we see is we have some options to filter the states that we see. We will look at that later. And then the main things that we can do is we can select the next state. So the environment starts with providing some input. So here we only have one option, and that is because there is an assumption that initially we have car A equals true and not car B. So of course then the environment is restricted to that initial assumption. So now let's select this state. Now let's assume that no further cars are coming. So we want to see what happens when no further cars are coming. So we can just double click again here on the false states a bit, and we see that there is always a system response because that's what the controller generates, and the controller keeps the lights both off. So let's give a few more no cars coming, and we see here that always the controller responds with keeping the lights off. That's reasonable, right? So now let's see what happens if we have cars coming. So now let's choose this one, and we see immediately after having a both cars on both streets, we see that the traffic light on street A is green and the one on B is false. So there is a guarantee, of course, here that they will never be true together. So that makes a lot of sense. And now let's see what happens if cars are coming again. Now we see both are off, and then the green one on street B, the traffic light on street B turns green. So it will basically do a round robin and then make sure we always eventually have the lights, both green lights on A and B. So the default behavior is that we are keeping a log. So the log, this checkbox here says generate a log. This is turned on by default, and this means that the states that we saw here, they are saved into a file, so we can later review the log. We can now maybe close here, and if we refresh, then we see that in the file system it actually created this log here, which is the states that that we basically walked through. Here the states are combined. They're always the environment variables, then the system variables. So we could start the controller walker again and then load that file. So let's walk again. It doesn't really matter for loading logs as who we are walking the controller. we just select the log, and then we can either always click here the next state, but now it's a combined state because there's no for log. We are not separating between system and environment. Also by clicking on next state here, we would walk through the next states until we are reaching the end of the log. So this is how we can also replay logs. If we say reset, then we reset the log, and we also reset the symbolic controller, and we can start again playing the controller. So let's stop this now, and now what we can also do is we can not only walk as the environment player where we provide the inputs, we could also walk as the system player or as both players. Now let's walk maybe as both players. Again, the initial state is fixed by some assumption. Then next we can select some states. And then we see suddenly that in some cases the system actually has multiple options. So here the system could turn on a green light or not. And these multiple options, this actually is the case because we have by default a symbolic controller that is not deterministic. So usually a controller should be deterministic. So if the environment gives us one possible input, which it always does, then we respond with a single possible output. But then playing as the system would not be so interesting because we could basically just choose a single option. But let's maybe see where we can turn on this determinization. So it is actually more efficient to synthesize a non-deterministic controller that is then determinized at runtime or simply by picking any possible state. So any possible system response that the controller allows is guaranteed to satisfy the specification. But if we say determinize the controller, so if we go to the preferences of Spectra and then say determinize the static symbolic controller, it would make sure that we only get a single system output for every environment state. So let's now synthesize the controller again. So then we can now again walk as both players, and now whenever we are the system player, we should only get a single option. So again, the environment is not really restricted. It could provide cars, either no cars, or it can provide cars on both sides. And now the system will always respond with a single option. If we maybe want to filter the states, so here we don't have many possibilities, but you can imagine that if we increase the number of variables, then this will quickly blow up. So what we can do is we can either choose a variable and filter by setting this variable to a specific value. So let's say we want to set variable car B to false, and we simply add this filter, then it would filter here only the states where car B is false. Now, if we want to do the same thing for car A false, then we would only get these states shown. These filters, they only apply to the player who owns the variables, of course. So basically now we are as the system player, and now these filters, they would have no effect because we are now entering different kinds of variables. But as soon as we are the environment player again, it would filter again based on this. We can remove filters like that, or clear. Then we can also do some more advanced filters. So we could, for example, say that we want to filter where we have car A or car B. So here the syntax that we can use is exactly the same syntax we use in Spectra specifications. So we can use this or we can use an implies, and then we apply, and then we always get the different filters, the different options filtered. So yeah, this way we would have at least one car if we put the or. then apply that filter. You can write anything. You can write almost everything that you can write in Spectra, so you could even use predicates here or other language features. You can also mix the variables, but there is some restriction here because let's say we want to say something where car A implies green A, and we use that as a filter. So this doesn't really make sense in the controller walker, because what happens is that the environment inputs and the system outputs, they will always be matched against this filter. But here car A implies green B if car A implies green A. If we only have the variable car A, then any assignment is possible for that variable. There's B, green A is basically a don't care. So here the filter on the environment variables only will not have an effect. And then similarly on the system side, it's basically here our choices will not restrict car A. So again, also on the system side, this doesn't really have an effect. Might be a difference if we have an end here. But basically for these filters, you should not really mix the different environment and system variables, because these filters, they always apply to the choices here only and not to the states that we're generating. If you want to be a bit more, if you want to do something on the states, then this will be the breakpoints, but that's another session. Okay. Then one more thing is, if we have a more complex specification, for example, this one here, I say it's more complex because we have the response pattern actually instantiated 3 times. And we have past LTL operators. So if we now synthesize that, the way that these features here are internally handled in Spectra is by adding auxiliary variables. So these will also show up in the controller walker because they might be of interest for the debugging. So let's have a look at playing this as both players. Now again, the inputs, that's the same, but then we see suddenly that we have tons of auxiliary variables. The names, they relate to the features. So for example, the 3 response patterns, they are encoded in these variables. And usually this is a bit, if we really want to debug what's going on, then maybe we are interested in these variables. But if we're not interested in these variables, we can simply disable them from being shown. And yeah, then it would show us the system variables, only the system variables which we really enabled. So this makes it a little bit easier to choose. In the log, they would still all appear so that we can replay the log completely. And you can, of course, also remove some of the environment variables, but then, you still have these are still separate states. So you see that the values are the same. Now you're just not seeing that they are different states, but they are different because we have here, I guess, where car A that is not shown is false, and here where car B that is not shown is false, because for the execution of the controller, we always need the complete assignments. So it's probably not a good idea to hide environment variables because we always would need to see all of them. We can hide system variables because for system variables, we might even just have deterministic choices. So usually just a single option, and then maybe we are only interested whether green B is true. So we only want to see green B. That's usually a good idea then. Okay, and now for this module would be to synthesize a controller from the specification grid L3 less Spectra, and then explore both players. So explore the specification as both players, and you should not use the determinization, because if you turn off determinizing the controller, you usually get more choices as the system, which makes some sense when you just want to explore the specification. So the specification is this one, which was used in module L3, but I have deleted some of the assumptions and guarantees to make it a bit more interesting to explore. It's basically the movement of a robot on a grid. And here the size of the grid, we have restricted it to 5 to make it a little bit more easier to browse. So the task was to synthesize. Okay, so now we will give another few minutes for people who want to follow the task before we continue with the solution. There's been a very interesting discussion also in the chat about whether we can synthesize different controllers or optimize the controllers for different tasks. For example, non-functional properties or size of the controller. So there are different other works, for example, that do bounded synthesis, where they try to find controllers within a certain bound or size. I think they don't scale well for these kind of specifications that we have with this synthesis fragment. But they work for, well, they usually outperform other approaches on general LTL synthesis. And yeah, as Shachar also mentioned, we have some work which is currently under review, which allows you to add some weights to transitions. So you could add weights to states where you say, well, if you are in this kind of state or partial states, like whenever the green light is on, this will cost you something, or it will reward you with something. You can add positive, negative weights. And then there are certain criteria for how the system needs to manage this value over the whole run of the system. So we're waiting for results on this one. But I guess if anybody's really interested, we can share more details, of course.
Thanks a lot. Yeah, I'm definitely interested in this work.
Okay, so I wonder, are there more questions right now? Does anybody need more time to explore the controller by themselves, or should we just go to the next? Should we just explore it here on the screen? Maybe we can just continue and show how we explore this controller with the controller walker. The controller for this specification, let's just first check that we do not have determinization enabled. So here we see determinization of the static controller is not enabled. That's what we want right now for exploring it. Then we say synthesize a static symbolic controller on this specification. We can just quickly check that it worked. So we see it worked. Of course, if you have some guarantee that says guarantee always false, then the synthesis will tell us that this is an unrealizable specification. And then there won't be any controller. So now let's see, we still have the previous controller. Now let's walk it as both players. And then we see that the environment initially is controlling the position of the robot. So initially the robot can be placed anywhere. Let's place the robot at 0, 0. Then the system can choose which way the robot moves. So let's maybe move down. And then we see that now the robot in the X coordinate still stays in 0, but in the Y coordinate has moved to 1, which makes a lot of sense. So if we go down again, we see it goes to 2. So now actually we are, that's based on the specification. The assumption was always here prescribing how the coordinates are updated. Okay, so now let's try some other moves. Let's move up again. Okay, then we go to 0, 1. If we move maybe left, which shouldn't work, we stay in this coordinate at 0. If we go right, it also increases to 1. If we stay, suddenly there is something strange going on. So now the environment could place the robot anywhere, which is not what we want to achieve by stay usually. So there is some issue here. If we try the other ones, we see there's always just a single option. So now let's close this and let's inspect the specification. We have actually forgotten to include the case for stay, and that interestingly was already in the previous version of the grid that we used in L3. We simply forgot that. The fixed predicate is basically saying that we keep the value fixed. So fix that coordinate. So sometimes it makes a lot of sense to just simulate the controllers a little bit and make sure that we didn't forget anything in our assumptions or guarantees. Okay, so let's have a look at some advanced language constructs. We will look at type definitions, defines, arrays, and predicates. So we will use again the same specifications as we had in L1, but now we're going to extend them a little bit. So yeah, let's start again with a traffic example. So if we want to express something like whether there's a car waiting, this might get a little bit complicated expression, and we might use it in multiple places. So if we want to reuse a complicated expression, we can simply do a define. A define has a name, so let's call it car waiting, and then we have this definition symbol, and then we have the body of the define. So the body of the define, when is a car waiting? A car is waiting when there is a car at A and not green A, or when there is a car at B and not green B. So we don't want this to happen to be written over and over in our text. So let's maybe always eventually say we don't have a car waiting. Sorry, this was the assumption. Let's move the assumptions just up here and use that as a guarantee. We always eventually don't have a car waiting. Okay. Now we could check whether this is realizable or not. And it is unrealizable because right now there's no way to make sure that basically the environment could always provide a car on A and B. So this means at any point in time, any car would be waiting. But this is how you could use defines, and you can put any kind of expression here. It doesn't have to evaluate to a specific Boolean value. It can also evaluate to other values. So here in our grid world example, we could I don't know, define something like the sum of the coordinates or something like that. So this would be define maybe coordinate sum, and then we could say rob x plus rob y, and then we could have a and of course we need the definition symbol, and then we could use that maybe in a guarantee that says guarantee always we want sum of the coordinates to be less than 7, something like that. Then the robot has to make sure to stay somewhere in a, well, kind of circle around the origin. Okay, but we actually have here only a single robot. Maybe we want to use multiple robots, and then there might be multiple moves. So we might have a move of a robot, and we might have a move of a drone. And now we have this repetition of the type, which is not so nice. So what we can do is we can also have a another kind of definition, which is a type definition. So we can define a type. So we can call a type maybe move and then assign it to everything we can set as a type. So we could have this enumeration, and then wherever we wanted to use that enumeration, we could use the type for it. Or we can even do the same thing for the integers here. If we want to only write that once, we could write a new type definition, and maybe we can call it a coordinate which goes in this range. Now if we want to extend the grid, we can simply do it in one place and set this to 20. But now we still have this robot X and Y. That's a bit, yeah, not that nice. We could also have something which is an array. So if we have an array of size 2 for the robot, then we don't even have to repeat that. So maybe we, yeah, then we would have to rewrite this to rob0 plus rob1. So arrays, they have, yeah, they start counting at 0. And basically the rob x would always be then a rob at 0, and the rob y would be the rob at position 1. And then the moves, they are also now, this might be, well, this would be the move rob. Yeah, and this way we could use the type definitions, we can use arrays and work with arrays, we can define them and we can access them. And yeah, then what is maybe missing still as one of the language features would be a predicate. So a predicate is something that we could instantiate. So let's say we want to define a predicate. A predicate has a name. So let's call it maybe fix, and the parameter might be something of type coordinate C. And then what this fix does is it simply says that C equals next value of C, and then we can use that in a guarantee. So we could have a safety guarantee that says always when we have move rob equals stay, this would imply that we fix rob 0 and we fix rob also at, well, the y coordinate. So this would be instantiating the predicate with different coordinates. And then we can check whether this is still realizable. It is unrealizable, and to understand why it's unrealizable, that's probably a bit more tricky. So this will be in one of the further analyses that we will do to understand why specifications become unrealizable. Okay, so the task here would be to extend the specification in grid L2 Spectra with the following predicate, where you have two parameters of type move, and you assert that these are inverse to each other. So if one of them moves up, the other one moves down, and if one of them moves left, the other one moves right. We can ignore the case of stay. And yeah, so this will be the task. So now let's have a look at the solution to this task. We had to define that we had to create. Just a quick update. So it's not that we have fallen asleep. We're just going to continue with the solutions if there are no questions. So if there are questions, we will stop. But otherwise, we're just going to continue. And the videos will also be, all of them will be available on a YouTube playlist. We might send some email with the materials after the briefing, so that if you want, you can still do all the exercises and then have a look at the solutions later. Create a predicate and say that the two parameters that it gets are of type move, and they are inverse to each other. So one goes up, the other one goes down, one goes left, the other one goes right. Let's see how to implement this predicate in our grid. So let's create a new predicate. Let's call it inverse moves. We have move A and move B, and then we can use a predicate maybe. So we can basically do this by using other predicates. Otherwise, we would have to kind of list the cases. So we have something like up down AB or up down BA or left right AB or left right BA, and then we need these predicates that we just defined. So predicate up down would simply say that A equals up and B equals down, and then we instantiate it here with both directions. So this is how we're checking that A and B are inverse in up down or down up. And then we need the left right, so we can create a new predicate left right, and this can be again move A, move B, and A would be left and B would be right, and then we could put this into some kind of guarantee, maybe an initial guarantee, or maybe an always guarantee that says inverse move off, and we instantiate it with the two that we have, the move rob and the move drone. So then the robot and the drone, they would have to move inverse to each other. We already had this thing unrealizable before because of this coordinate sum here, so let's remove that now and check realizability. Can't resolve left right because this doesn't exist. Now it should look better. Yep, now this is realizable. And if we synthesize a controller, we will probably have to wait a bit. Oh, but we should see here, at least just by quickly looking at it, they look quite inverse to each other. So, oh yeah, there's a lot to look at. Okay, So I guess we can trust this. So this would be the solution. I mean, you can spell this out in a single predicate where you do all the case distinctions here. Basically repeating this with both directions and then repeating that with both directions. But you see that you probably have a use of this predicate here in inverse move instead of repeating all the case distinctions all the time. So now we're going to have a look at unrealizability of specifications, and that is the case when there is no way to find an implementation for the specification. So if there would be any kind of implementation for the specification, then the synthesizer would find it, but in some cases there is no such implementation. And we're going to look at how we can check realizability. We already did that. And then also how to compute an unrealizable core and counter strategies. So here we have some unrealizable specifications. There is this traffic A1B that we had earlier, and it was unrealizable. So let's have a look. Check realizability tells us it's unrealizable. Now, what do we do to analyze this? We see unrealizability. Well, it can't depend on variables. It must depend on some assumptions and guarantees, and most likely, or in all cases, it is a problem of satisfying the guarantees. So either the guarantees are contradicting each other, or the assumptions are not enough to let the system satisfy the guarantees. So the first thing that we can do is we can compute a core, which is a minimal subset of the guarantees that is together already unrealizable. So, I mean, here we have 5 guarantees. So let's see if we can minimize that. We can go to Spectra add-ons cores and then say find an unrealizable core. And this finds a small subset of only 2 guarantees, and it tells us that these 2 guarantees together are already unrealizable. So let's have a look, and we saw that this was here. This is the safety guarantee that says that the 2 traffic lights are never green together. And then here is a liveness guarantee that says that always eventually the 2 traffic lights are green together. So, well, there's a clear problem here. We can't even satisfy these 2 together. So this is now, well, these 2 expressions here. So the this we could already find out by just looking at whether it can be satisfied together, that green A and green B are true and not green A and green B are true. So we clearly see that can't be satisfied together. So this was a simple case. Now let's look at a little bit more challenging case. Let's see here if we again check realizability. We see it's unrealizable. Now we even have 6 guarantees. Now let's see if we can find a core. Find some unrealizable core. Oh, it is, this core has a single guarantee. Well, that's not very helpful. So this means that this guarantee doesn't conflict with any other guarantee. It means that the assumptions are not strong enough to realize this guarantee. So now if we want to see how, if the assumptions are not strong enough, this means there is some environment that will prevent us from realizing these guarantees. So we can ask Spectra Tools to compute such an environment for us. And this environment would then be a counter strategy that will prevent any kind of strategy that we could think of to realize this specification. So let's have a look. We can go to Spectra and then synthesize a concrete counter strategy. And here we see what the environment can do to prevent us from realizing these guarantees. So the one of the guarantees that we can't realize with this, that we have a car at A, and also we have a green light at lane A. So let's have a look what's going on. So initially there is a car in A, and we go to state S0. When we are in state S0, there's no longer a car for A. We go to S1, and in S1 there's also no longer a car for A. So basically what happens is that the assumption, this liveness assumption here, allows the environment to always go for the alternative that there is only a car for B. So there's nothing that says that there will always eventually be a car for A. So that is why the environment could simply only send cars on B. This would satisfy this assumption. And we have no way of realizing this guarantee that we can have a car passing on A because there's no car coming. Okay, so these are the two main ways of understanding unrealizability. First, we can of course always check realizability, and then we can compute either a counter strategy, or we can go to the add-ons and compute one unrealizable core. And yeah, there are different options here as well, all unrealizable cores and further options also. Now let's have a look at, there are 3 more specifications here, and the task would be to analyze these specifications and to understand the reasons for unrealizability using either the core or the counter strategy. So both of them have their rights. So if, for example, if the core is just a single guarantee, then probably we need a counter strategy if we still don't understand the reason. Or if the core is very large, this could also happen, that it might make sense to have a look at the counter strategy. Okay, so let's have a look at the solutions for these tasks. We had to analyze these 3 specifications, B, C, and D, and understand the reasons for unrealizability using a core or a counter strategy. So first we should always check whether they're really unrealizable. So this one, well, we only have 3 guarantees, that can't be so difficult. It's unrealizable. Okay. Let's see if the core tells us anything. There is a core of a single guarantee. This guarantee says always eventually we have a car on A and green A. And we say we never have green A and B together. So let's have a look at the counter strategy. So the core really just had a single thing here. So let's have a look at a counter strategy. The counter strategy is also quite simple, and just by looking at it we see that the environment always gives us false for cars on A and cars on B. So there's never any car coming on A, never any car coming on B. So we're clearly missing some assumption here, or maybe something is wrong with these guarantees, that they are not the right guarantees. But that's not the question right now. The question was to understand why it's unrealizable, and here it's unrealizable because there's no way we can satisfy this guarantee, and there's also no way we can satisfy this guarantee because there's simply no car coming. Okay, now let's look at the next one. So check realizability again, it's unrealizable. Now let's calculate a core to narrow down the problem. Oh, that doesn't narrow it down so much. It's simply all of the guarantees. So let's see if the counter strategy tells us anything. Well, at least the counter strategy is really simple. The counter strategy would send always a car on A and always a car on B. Now let's see why would that be a problem for any of these guarantees. Again, we can never have green lights at A and B at the same time, otherwise the cars might crash. And then it says always eventually we have to have a car on A, which implies that we also have green A. And now we see that here car A is always true, which means that really to make this implication true, we always eventually have to have a green light on A. Now we also have always a car on B, and here it says when there's a car on B, we just need to have the green light. So this is an always, not an always, eventually, which means that this basically has to hold in every step. So in every step, we need to have a green light on B, and together with this, that we can't have a green light on A and B together, we are basically forced to violate this, either this liveness guarantee, or we are forced to violate this, this safety guarantee, or this safety guarantee. So basically, that's why the core is so big, because all of them together, they force us to not being able to realize the specification. If we would remove any of the guarantees, then the specification would be realizable. That is a property of the core, because the core is always minimal. Okay, this was C, and the reason here was simply that if we have a car always coming on B, then there must be a green light on B, and then we can never have a green light on A because of this exclusion here. So that is why we have to violate this liveness assumption. Now let's have a look at the last one. We start again by checking realizability. It is unrealizable. We can try to compute a core. Again, it's all of them. And now if we check for a concrete controller, that was a concrete controller. So if we check for a counter strategy, then, so this is actually a little bit of a tricky case, because it says that we will be forced to a deadlock, but what we don't see is the outgoing transition that really forces us to the deadlock. So what we see is here, initially there is no car, and then no matter what we do, we end up in a dead state. But the reason why the state is dead is not really visible here. What happens in this state is that both cars will appear. We have both of them true. This means that green A must be true, green B must be true, but that's not possible. So this is how we basically deadlock the safety. We have a kind of deadlock through our safety guarantees. So we have previously seen how to look at the controller that we synthesize by looking at the concrete controller. Then we've seen how to simulate a controller using the controller walker in case of a symbolic controller, but now we also want to look at how to execute the controller of our reactive system to actually have it run in some piece of code. So what we will do is we start off again with a specification. Here is a simple traffic light specification. It has even some assumptions and guarantees removed to be the very, very basics. And now to simulate this, we will use a symbolic controller, but now we will use the just-in-time symbolic controller because this scales better for even larger systems. So we will now synthesize a just-in-time symbolic controller, and we will see the out folder appear. And now the out folder has a little bit of different files. But now we don't want to load this in a plugin. We really want to run it programmatically. So we will have a look at a very, very basic command line based simulator. And what we need to do is we first need to read the inputs that the environment would usually provide us. And then we need to feed this to the controller. And eventually we will read the outputs that the controller produced. So in our case, this is the whole application that loads the controller. It's just 60 lines of code, and the main lines of code that we need to look at is the controller executor. We need to load the controller from this folder out. That's always very much the same line. The only thing we need to add to the build path of our Java application is this executor.jar. We might want to have the native libraries UDD or the Linux-based version. We don't really need these. It will also work just pure Java-based, but it will be a little bit faster if we have these native libraries. But the main thing we need is this jar file. We add it to the build path and then the controller executor that is from this jar file. So this line is important, and then what we need to do is we need to feed the controller with the inputs. So the way we feed the controller is always string based. So we give the names, we give a map of the name of a variable and the value of the variable. So all the input variables, we can put them in a map inputs, and then we can tell the executor that this is the initial state when we run the executor when we execute it for the first time. And if it's not the first time, then we just say update state, and then that's the current inputs received. Update state and initial state will do the calculation to calculate the outputs. We can simply ask the executor for the current value of the specific variables. So here in this case we had the environment variables car A and car B. So these are our inputs. This is what we put in the inputs, or in the map of the inputs, with the corresponding values. They are Boolean. So here we put simply true and false, or the Boolean to string basically. For enumeration values, you would put the string of the enumeration value. For integers, you would still have to put the integer to string version like we do here for the Booleans. Yeah, so this is how we provide the inputs, and then the outputs, we simply ask the executor to get us the outputs. And that's it for executing the symbolic controller. So all the other stuff that you see in this file, this is just, we start by printing whether car A is present, reading the next line, converting this to a Boolean, just to show you how it would work if you want to feed your controller actually with the real data types, the Boolean here in this case. So we get two Booleans for car A and car B. Then we feed this to the controller, and then in the end we read the values, and then based on which values are true and false, we give some outputs. So now let's execute this. We have synthesized the symbolic controller. Now we can run this traffic simulator simply as the main method. So question is a car present for A? Let's say there is one. Let's say there is one for B. Then it would allow car B to go. Now let's continue. Cars are again both present. Then it would allow car A to go. So here, yeah, the default, I'm simply checking whether it's N for no car there. So now let's put N, no car. Car A would still be allowed to go. That's fine. All cars must stop now. Yeah, if we don't have cars, this controller will have the car stop, but there's actually nothing that requires this in the, I think there's nothing that requires this in the specification. The only thing we want, again, that there are no cars on green A and green B. So yeah, this is how you would integrate it into an application, and we have here integrated it into an even a little bit more visual way. So let's stop this one on the command line, and what you see here is basically, again, inputs and outputs. Again, this is the first time we load the controller, and then we say the initial state is based on these inputs, and then again we have this loop that just now takes random car A and car B inputs, gives them to the executor, and then takes the green A and green B as outputs. So if we want to run this one, this is a bit more fancy. Then we will soon see the cars coming. So now there's no real input-output. Well, there is input-output for the controller, but now it's not interactive based on the user, because here we just generate random inputs and outputs when the cars are there. But as you saw in the previous example, we can, or we should usually have it based on inputs or events or other data that comes in from other systems. So that's, for example, when we run it on robots, then the inputs that we give to the controller, this would really be stuff that we measured using sensors and abstracted then to the the kind of values that we need for running the controllers. Now, the task for this would be to extend the specification that we had here in E2 and extend the execution with an additional input variable emergency, and then a guarantee that in case of emergency, both lights are red. So this emergency would be a Boolean variable, and the extension would have to happen in the specification. So here you would have a new environment variable with the emergency, and then you would have a guarantee that if emergency is true, then green A and green B are both false. And the next step would then be to extend the command line simulation to handle this new input. So instead of taking the two inputs of car A and car B, we also take the emergency input and feed it to the controller. So this would be the task. Okay, so as the solution of this task, we're now going to extend the specification with this new input of an emergency variable. So this would be an environment variable of type Boolean, and it will be called emergency. And then we would say that there's a new guarantee. So this would be another safety guarantee. Always emergency would imply that not green A and not green B. Now let's see if this is realizable. It's unrealizable, and the reason is that we could have this, we need always eventually green B, so a counter strategy could probably be that we always have emergency, and then we would never have this green A or green B. So here one way to fix this would be to say, well, if we have emergency, then we don't need the always eventually green B or the green A. Now let's see, it's now realizable, and we can now synthesize another controller. And now we need to extend the controller runners. So if we, the command line based one, now if we run this command line based one and we simply say car is present, then it will probably just ignore the value. It will give a default value to emergency, but that's not actually what we want. We want to actually also read the emergency value. So let's extend our creation of values. So this would be simply the new variable emergency. Do we have an emergency? And this would have to go as another input to the controller. Okay, so we only extended inputs. That's fine. Now let's see. So let's put a car there. And let's say we have no emergency, then we see that car A is allowed to go. So now let's put again cars there and say that we have an emergency. Then all cars must stop. We have again cars, we have again an emergency. Again, all cars must stop. We have again cars, we don't have an emergency. Now car B is allowed to go. Okay, so this is the extension. We have simply extended the specification with the additional variables, some additional guarantees and updates of guarantees. And then the main interesting thing here was actually this single line that extends the inputs by providing the new input that we have just read and giving it to the controller. Okay, now we're going to look at advanced language constructs, and we're going to look at patterns and past operators. So patterns, they are ways to group different constraints and even have some kind of private variables defined. So a pattern is usually defined in with its own name. Then it has different parameters. This can be expressions that evaluate to Boolean values, and then we can define internal variables of a pattern that they can keep, then some where they can keep, for example, a state of something. So they could monitor some state and decide what to do based on this state monitoring that they do, but they are much more powerful than just state monitoring because they can have initial, safety, and liveness constraints inside patterns. So you can do very powerful things with patterns, and we showed that you can do quite powerful things. For example, the combination of these LTL operators, and you can express them into patterns, and we've done this automatically for some patterns. So they are quite complicated LTL formulas that you are able to express into these GR1 patterns just with the usual GR1 constructs. And the patterns that we see here in this pattern catalog, they are taken from Dwyer patterns, so they are known as the LTL specification patterns. And most of them are supported in Spectra through this pattern mechanism. But you can also define your own patterns. So this is the way you define patterns, and then of course we would like to instantiate them. So there's a very interesting pattern here, the response pattern, S responds to P. So we might want to use that pattern and instantiate it for our traffic light example. So in our traffic light example, we might want to have a guarantee that S responds to P. The two parameters are, first parameter is P. So if we have a car in lane A, then we want to respond to it with a green light on B. And now this response is not necessarily an immediate response. So what can happen is that this response will only happen after a few more steps. And this is very powerful because this allows us to simply instantiate this into a single line that we say, well, sometime after this happened, after there's a car on A, we guarantee that there will be a green light on A. And we can do the same for B, of course, that after there was a car on B, we guarantee that after some finite time, always when there's a car on B, after some finite time, there'll be a green light on B. And if we check now if this is still realizable, yep, it is. And it can give us a controller. And this controller is a bit more complex than it was before, but this is because it keeps track of whether there is the need to turn the green light on each of the streets, and it has to keep track of this because it can't turn them on at the same time. So there are some other patterns here. So maybe in our grid world we have now some positions defined, basically the corners, corner 0, 0, then another corner and another corner with these positions, and we might want to say that we want the robot to always return to this corner 0 in between visiting this position P2 and P3. So there is another pattern for this. Let's see, there's, for example, this P becomes true between Q and R pattern. So let's try to instantiate this here. We would have we instantiate it again as a guarantee, but you could also instantiate patterns as assumptions. The important thing is you don't use any temporal operators because the patterns have temporal operators inside. And then P becomes true. So let's have P1, we want it to be true between visiting this P2 and P3. And now if we synthesize a controller for this, then let's first check realizability. It is realizable. And if we synthesize a controller for this, then this controller would visit P2 and P3 and always make sure that it visits P1 in between. So yeah, it's a little bit too large to look at now, but yeah, you can try it on a smaller grid maybe. Okay, so this is the patterns. Now there's also another thing called past operators. I mean, in Spectra we have the temporal operators that we saw previously. We have ini that just relates to the initial state. We have always that relates to any state, and then we have always eventually that relates to infinitely many states in the future. And there are also other temporal operators, for example, previous or historically or once, and these are past operators. They relate to some point in the past. So if we wanted to write a guarantee that always, or maybe an assumption that always eventually once, we can write once like this. There was a car at A, then this would be the assumption that at some point in the future, if we look at the past, there was once a car on lane A. So this once, the past operators, they are described in the user guide. You can write once typed out, or you can just write O. So maybe let's just have it fully typed out. And then there are also other operators like historically, so we could even nest them, which we can't do with the other temporal operators in Spectra, but past operators we can nest. So this means that once historically, so historically refers to from the current point of time back to the beginning of time. But now this is in the context of once. So this means that there's some period at the beginning of every run of this system where car A was true. Okay, and then you can also do other things where you could, for example, have another operator called previous. So we might have a guarantee that always, if we have green A, this implies previous green B. Something like this you could write with past LTL operators. Okay, and the simple task for this would be extending the specification of the traffic light with a pattern in an assumption. So patterns in assumptions, they are just the same as patterns in guarantees. You just put in the pattern in assumption instead of guarantee and instantiate it the same way. So here we need to add an assumption that car A is always eventually followed by car B, and you can do that with the response pattern. Let's just have a quick look back. So we use the Dwyer patterns and we have to import them. So if you want to use them in a specification, you need to copy the Dwyer patterns catalog and into some directory that is reachable from your specification. So you can also use ... and path navigation, but this way you can import collections of patterns, for example. So let's have a look at the solution of this. The assumption that car A is always eventually followed by car B in our traffic. So here we would add maybe let's add it at the bottom, an assumption, and the response pattern was this. And we simply want to say that A is followed by B, so whenever A happens, then eventually B has to happen. And yeah, this is already the solution, and the specification is still realizable like this. So welcome to this session. Okay, great. Yeah, so there was a question in the chat about whether patterns are something abstractions similar to methods in programming languages. So there is not really this close parallel to these mechanisms in programming languages. So patterns can be instantiated. So they're basically helping you to write less, and they encapsulate like the meaning of this LTL, a more complex LTL formula. Like predicates, they are abstractions of more complex expressions. And in terms of modularity or anything, we have only this import mechanism of patterns, but there is no modularity in terms of defining different parts of a distributed system. So this is the research, even the research on synthesis for for distributed systems is still ongoing, and there are many undecidability results already. So in general, it's not possible. But yeah, there are ways. For example, if you have a distributed system, you would have to break it down into the assumptions that, like, basically the assumptions would then refer to all of the parts that are outside the one system, the one controller that you are trying to synthesize. Yeah, so there is no other mechanism right now, but yeah, you could imagine that in a larger environment, you work on some transformations that manage this. Okay, are there any other questions? So if you saw the outline included 2 more sessions, but these 2 sessions, we will make them available for everyone in YouTube videos with the solutions, and the code is already available to you. And now we will conclude with yeah, a quick set of presentation slides.
Yes.
Shahar, do you want to? Yeah.
Yeah. So let us end this tutorial with a few final notes. First, about what's next. So Spectra can be used as a testbed for future research on reactive synthesis. And in future research, I mean on means to write better specifications, to help engineers write better specifications, means to analyze specifications, and of course also to executing the resulting implementations. So all these things are things that we already do, but in all these 3 directions, there is a lot of work that can be done to improve stuff. The Spectra code is available on GitHub. You can find it there. And we've made the example, some more example specifications and applications available on the Spectra website that you can try out. And finally, we're very much looking for collaborators that work on anything from case studies and applications to just use Spectra to do something. And of course, also to contribute from within. So to consider additional language constructs, better analysis. So please feel free to contact us about that. And yeah, with that, we want to thank the students and postdocs who have contributed to Spectra and to the preparation of this tutorial. Thank you to all of them. And thank you all for attending this tech briefing or hearing this recording later on. We hope you found it interesting. Take care, and we hope to see you again sometime soon in a future real physical conference. Thank you.
A lot. It was very useful.
Okay, thank you so much, Cesar and Jean-Oliver, and all of you, the attendees. And with this, it's time to close the technical briefing. And that's all from my side. Please, Cesar and Jean-Oliver, close the recording at your earliest convenience and send me the link once it is done. Thank you so much, and enjoy the rest of the conference. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye. I don't know if